Hey everyone, and welcome. If you are an engineer working in the power electronics or automotive space, you already know the ultimate bottleneck we're facing right now: safe, high-speed EV charging. Everybody wants faster charge times, right? But pushing massive amounts of power into a battery pack without, literally melting the infrastructure, that is a monumental engineering challenge. So today, we are doing something incredibly exciting. In this explainer, we're going on a reverse engineering journey of a highly optimized 800-volt DC-DC converter. And we aren't just talking theory here. We're breaking down a dual simulation validation using both MATLAB and Proteus. Okay, let's dive right in. Here's our roadmap for the explainer today. First, the 800-volt charger architecture. Second, topology and component selection. Third, resonant tank design. Fourth, hardware simulation in Proteus. Fifth, control simulation in MATLAB. And finally, the future of fast charging. Let's get started. All right, section 1, the 800-volt charger architecture. Let's set the stage. Just look at the sheer scale of the power we are managing here. We're targeting a massive 800 volts DC output, 80 kilowatts of power, and an output current of 100 amps. And check out that efficiency target, greater than 95%. These aren't just arbitrary numbers drawn out of a hat. These specific high-voltage parameters are precisely tailored for modern, fast-charging EV battery packs. And to actually achieve that greater than 95% efficiency at a 50 kilohertz switching frequency, well, every single stage of the conversion process has to be perfectly optimized to minimize thermal and switching losses. So how do we get there? Let's track the power flow. We kick things off with a standard three-phase 220-volt AC input from the grid. Our first major stage is rectification, which flips that AC power into an intermediate DC bus, giving us roughly 200 to 450 volts DC. But remember, our target is an 800-volt battery pack. So the final step, and really the star of our show today, is processing that rectified DC power through a highly controlled DC-DC converter to achieve a super stable, clean 800-volt DC final output. Moving on to section 2, topology and component selection. How do we build this beast? For our core architecture, the source material relies on a buck converter topology. Now, for the expert engineers tuning in, you might be wondering why we lean so heavily into this specific topology for the final regulation stage. Why not alternative charging concepts? Well, compared to things like non-isolated linear designs, which would just be ridiculously inefficient at this scale, a properly implemented buck-based architecture lets us precisely step down and regulate that post-rectified grid voltage to perfectly match the dynamic real-time requirements of the EV battery. Basically, it gives us the control authority we desperately need to prevent things like thermal runaway. And this brilliantly illustrates exactly what is under the hood, making that topology tick. First up, we're using IGBTs. Why? Because at 80 kilowatts, standard MOSFETs are going to struggle with conduction losses. IGBTs are chosen specifically for their high voltage handling and lower conduction losses at these massive power levels. Second, we integrate transformers with a highly specific 0.25 turn ratio. That gives us vital galvanic isolation and voltage scaling, which is a crucial safety and performance metric. Finally, snubber circuits are deployed across our switching devices. At these power levels, a rogue voltage spike can destroy a circuit instantly, so snubbers are strictly required to eat those spikes and minimize switching losses. All right, section 3, resonant tank design. Time to get into the math. I want to anchor our narrative right here on this number, 50 kilohertz. This is our switching frequency, sure, but more importantly, it is the target resonant frequency driving the selection of all our passive components. The impact of this resonant circuit is massive. By tuning our system to 50 kilohertz, we enable soft switching that drastically reduces power dissipation while simultaneously setting the baseline for our electromagnetic or EMI filtering. Basically, it ensures the AC noise generated by all this high-power switching doesn't corrupt our clean DC output. So how do we hit that 50 kilohertz target? Well, we've selected resonant capacitors at 6.4 microfarads and resonant inductors at 39.56 microhenries. This very specific L and C combination, operating alongside our 0.25 transformer ratio, results in a calculated quality factor, or Q factor, of 0.2018. It's this specific mathematical harmony that achieves the required 50 kilohertz filtering, keeping our ripple constraints perfectly in check and optimizing the thermal management for the entire converter. Which brings us to section 4, hardware simulation in Proteus. Time to test it. We need to clearly delineate the role of Proteus in this design process. Proteus isn't just drawing neat lines on a screen, it is specifically used as our proving ground for visualizing real-time hardware readiness. And hey, quick practical troubleshooting tip for you simulation engineers. Always make sure your simulated component ratings exactly match your physical hardware constraints before running the test. Otherwise, the simulation will crash just like a real circuit would literally burn up. Proteus lets us visualize the continuous charging curve, ensuring that the voltage smoothly and safely ramps up to our 800-volt target. And speaking of safety, beyond just proving we can hit 800 volts continuously, Proteus rigorously tests our protective measures. We are simulating severe overvoltage scenarios, testing the overcurrent safeguards, and evaluating our thermal protection reliability. Guys, in an 80 kilowatt system, robust thermal and overcurrent protections are non-negotiable. If a fault occurs in the real world, these simulated safeguards prove the hardware will properly shut itself down rather than causing catastrophic damage to the grid or the vehicle. Moving on to Section 5, Control Simulation in MATLAB. Let's look at the software side. I absolutely love this summary directly from the source material. MATLAB ensures tight voltage regulation and dynamic load response. Think of it this way. Proteus is testing the muscle, and MATLAB is testing the brain. MATLAB provides the rigorous, high-fidelity environment we need to test the intelligence of the charger, specifically by utilizing precise pulse width modulation, or PWM, feedback control. Let's break down exactly what MATLAB is modeling here. It processes precise PWM voltage feedback loops, tracking the DC battery terminal voltage in real time. And what's really brilliant is seeing how the MATLAB outputs dynamically adapt to the EV's wallbox state. As the battery charges, its internal resistance constantly changes, right? MATLAB validates that our DC charging current continuously adapts to maintain absolute stability. Oh, and here is a practical troubleshooting tip for MATLAB simulations. If your output voltage looks totally erratic, go check your AC noise filtering simulation blocks. If the filtering isn't properly tuned to that 50 kHz frequency we discussed, your feedback loop is going to chase phantom noise, and the simulation will fail. And this really brings our entire dual simulation strategy into focus. On one side, Proteus guarantees the physical hardware, the thermal limits, and the overcurrent protections won't fail under the immense stress of an 80 kilowatt load. On the other side, MATLAB guarantees that the control logic, the PWM feedback, and the noise filtering properly manage and intelligently guide that power. By combining both, we eliminate our blind spots before a single physical component is ever soldered. Finally, Section 6, the future of fast charging. Let's zoom out a bit. The ultimate takeaway for all of us in the engineering field is right here. By combining rigorous mathematical design with this kind of dual software validation, we can create highly optimized, 95% efficient, 800-volt DC-to-DC converters. This approach successfully bridges the gap between theoretical simulation and real-world implementation. It proves that we can achieve the incredible high power density and system robustness required to build out the global high-speed charging infrastructure of tomorrow. So I want to leave you with this provocative question to chew on. As we scale these technologies, how will highly optimized, dual-validated DC-to-DC converters shape the next generation of smart charging grids? I mean, when the hardware is practically guaranteed to succeed before it is even built, the speed at which we can evolve the global EV network is limitless. Thank you so much for joining me on this explainer today. Keep pushing the boundaries of engineering, and I'll see you next time.